today we're going to be talking about parallelism strategies and what these fancy terms mean, like, let's see, like we have DDP, TP, and bits like that. So if you have questions, feel free to direct them into the chat and I'll answer them occasionally throughout this entire thing. But let's get started. So first, let's chat about DDP, which means distributed data parallelism. And the idea with DDP is it is designed solely to increase the throughput when training. So it's not one of these strategies where we do some sort of fancy model splitting. Instead, we have replicants of our model that exist on every GPU. So we're going to say this is Model 1, Model 2, Model 3, Model 4. Then what we do is, let's say I can only fit a batch of 8 on each GPU with my model, right? So my local batch size is 8. Well, DDP says since we're running multiple versions of the model at once, and they're all allegedly the same, then we can describe our global batch size as n times g, right? N being the local batch size, g being the number of GPUs. So we run these replicants across every GPU, get their outputs, and average the gradients at the end before we do our loss function. And this way, we have a large batch size while essentially just replicating the model itself. Now, the pros of that is this is strictly a benefit for increasing your batch size and increasing throughput, right? Because on average, you'll see some dimension of speed up when you're doing DDP. It's not exactly like a 2-to-1, 3-to-1, 4-to-1, because you're going to have some overhead from trying to deal with like communications, for instance. But it's pretty close. So the next level that we have is ZeRO, or FSDP. Now, ZeRO and FSDP strictly aim to take your model and have it fit better in memory. So let's take our model again, for instance. And let's say that the model weights are about, we'll say 12 gigabytes. So in half precision, 12 gigabytes total for the weights. And then if we think about everything else that comes along with training, you have the gradients, which generally is the same size. So that's our gradients. And then we have 24 gigs from the optimizer states, because Atom carries 2 momentums. So in total, we have model weights, and then we have gradients, mg, and then we have O1 and O2. Now, what ZeRO stands for is the Zero Redundancy Optimizer. And essentially, we, at the cost of communication, increase the throughput. It's combined with data parallelism to make training faster, but for using resources in a case of you imagine all of your GPUs as one big GPU pool rather than I have 30 3060s that I'm running on, which is the case of distributed data parallelism. Now, the way it works is you have 3 different stages. The first stage, actually, that's incorrect. We want to start at the bottom, not up here. The first stage is 0, 1. And the idea is you take your optimizer states specifically, and we shard them across GPUs so that each GPU only has a tiny amount of memory that's being used. But because it's at the optimizer state, we're not adding a lot of communication overhead because only the optimizers need to be updated to stay in sync. So it's low communication, but also low memory gains because it's just the optimizer states and not really helping with the other parts of it. Now, typically, what people prefer to do instead is 0, 2, which takes the optimizer states and the gradients and shards them as well. And what you get by doing this is every single GPU will have a full copy of the weights with everything else being sharded. And what happens with that is pretty much everyone can run independently until it gets time to go through and make sure that everyone's running with the same weights after you've run backprop. And so as a result, these two, right, so the optimizer state updates require a decent amount of communication. Not a lot, but a chunk. 0, 2 requires just a hair more communication, but the way it does the communications makes it more efficient, essentially. Then we have 0, 3, which is typically regarded as the slowest method of the three, but also it is the most memory efficient. You can take a wild guess what's going to happen here. We're going to shard the model weights themselves. Now, what that means is because the model weights are sharded, there has to be communication as a input, goes through the weights, right? The output from here needs to go to the output from here and vice versa, as we're dealing with sort of these interlocking weights as the memory gets offloaded. So the good news is, right, so if we think about the entire memory being used, so full training would have taken 48 gigs per GPU. 0, 1 gets us to about 30. 0, 2 gets us to about 16. And 0, 3 gets us to about 12, if we consider how everything is looking. Also, sorry for my chicken scratch. And so basically, it's the idea of adding communication at the cost of, the cost of adding communication with the benefit of reducing memory. Typically, these are compounded with ideas like InfiniBand. So what you can do is, since 0, 2 just shards 2 of the states, essentially, all the weights live on each GPU, and then communications can happen very, very quickly within the node to do all these updates. A scale above this is doing something called hybrid shard. So you run 0, 2 locally on every single individual node. And then to make sure that you're not needing to run communications between node every single step, because intranode with InfiniBand, you've got terabits per second of data transfer. From each node to each node, you've got, at most, I think we're at 100 gigabit Ethernet. So that's 12.5 gigs a second. You want to reduce that as much as possible, which is where the sort of hybridization approach comes in. Because communication does have a cost, even if you're using, say, InfiniBand and those magic things, your slowest point will always be communication between nodes. Now, the next idea is what we call pipeline parallelism. And the general idea of pipeline parallelism is, rather than sharding the model, I'll zoom out a bit, slide over some. So rather than sharding the model, we just partition it instead. So we're going to do the same thing where we have 4 different chunks of the model weight. So P1, P2, P3, P4. However, unlike ZeRO, we're going to have essentially smaller optimizers and smaller localized gradients for each partition. With the idea being, let's say this is GPU 1, GPU 2, GPU 3, GPU 4. If you've ever investigated pipeline parallelism, you're about to see a pretty straightforward diagram that you guys are probably familiar with. So in GPU 1, we always send the input. So we could call this batch 1. This will always be the first input. Then, after GPU 1 has calculated its localized gradients and so forth, and its outputs, we then send that batch to GPU 2. And then it does everything relative to its local parameters. Then we have, actually this is B1, and B1. So then after we've gone through and passed the parameters to every GPU, so this is the forward pass, then we have the backward pass, where we do the backward pass for batch 1, backward pass for batch 2, backward pass on GPU 2, GPU 3, and GPU 4. Now, what you get with this is essentially our results, right? The backprop happens over here. And then on top of that, we get the final loss calculation at the very end. And then we can fully update the weights, perform backprop, and make sure everyone's good. This is particularly handy because there's no needing to wait for the other nodes to do anything or make sure that outputs are aligned in certain ways. The second GPU 1 is done, goes to GPU 2. Meanwhile, the second it goes to GPU 2, this GPU is open, so we can process another batch. And then this chain continues, right? All the way up to GPU 4. This is just a small visual to make it understood a hair. And so this is really handy for training because it's quite fast, but it's also really handy for inference because during inference, we essentially cut it off here, right? Because we don't need backpropagation for working with inference. So you can handle a lot of inputs at once by feeding everything through the first GPU. You don't have to wait for all the inputs to finish and whatnot. It just goes directly to the end. And so that's sort of the idea of pipeline parallelism. It's a bit more efficient strategy than having to do ZeRO and waiting for everything to get done through the communications that it relies on. We're going to take a small side trick. There's a really good question by Tommy. What tools can we use to diagnose and see how much we're using interconnect bandwidth? Do we just have to estimate it by calculating how much memory our optimizer gradients and weights take? Or is there a tool that can monitor passing data between nodes? Is this info captured in Torch Profile, or do we need another profiling tool? Torch Profile and NVTop, as well as just running your own timing benchmarks, so seeing how long it takes for a batch to happen. You'll know right away, because there was a Twitter conversation a few weeks ago where someone was renting H100s, and they were finding that during their training, each step took 2 to 3 seconds. And then they found a different provider, same provider, but this provider had everything on InfiniBand instead, and it took a second per batch. And so immediately I know that they're not using InfiniBand for those particular nodes, because training should be 2 to 3 times what that actually is. Otherwise, Torch Profile is a really good way to capture this as well. It's a good way to capture whether or not certain matrix multiplications and whatnot are happening as efficient as possible. And it's a really good profiling tool in general that, in my opinion, you should kind of always be doing before you scale to oblivion. All right, so next up, we have tensor parallelism. Now, tensor parallelism, if we think about pipeline parallelism, real quick, it's a vertical slice of the model, right? We are taking individual groups of layers and slicing the model accordingly. ZeRO operates in the same fashion. Tensor parallelism is the exact opposite idea. So say we have, let's see how this renders, model M, and we'll say that particular layers take a lot of memory. So we'll say it has, 5 layers. This will be fun with the math, so we'll break it down to 4. So we'll have 4 layers, and we'll say each layer takes up 120 gigabytes of memory. Really, really big model, just for the sake of visualizing this. Rather than splitting by chunks of layers, which is far too big for that 120 gigs, we're instead going to split the model at the layer level. So each GPU gets a chunk of that particular layer that it's operating on at any given moment. And so what this does is it reduces the overall memory usage whenever, or partitioning per se, when you're training super large models that you could then combine with, say, ZeRO to make training more efficient. And essentially how it works is an input will be passed to each partitioned layer, and then all of the layers gradients get averaged. So it allows us to get to roughly the same equivalent, actually not even roughly, it is the equivalent to if we had the entire layer at once, but instead we can chunkify it to make things more efficient for our GPUs and train models far, far too big. Mert has a question of, can we see this sort of toolage for speeding up in weights and biases? So weights and biases lets you see overall GPU memory usage, and then you can track the speed at which things are happening, and you can measure what are called T-flops as part of your memory metrics. And so you can follow, Stas has a good guide on, Stas Beckman has a wonderful guide as part of his ML engineering book, where he has benchmarks that specifically measure T-flops. So you can run that T-flop measurement locally, see what T-flops you should expect for your model, and then you can run your entire pipeline and measure the direct T-flops as part of your metrics, and you'll know, A, just by looking at the T-flops and what he has found for particular configuration setups, are you getting the proper T-flops for your config, or is it not using NVLink and instead it's using, or InfiniBand, instead it's using PCIe? And then also you can see if there's any optimizations to the training loop, the data loop, and whatnot, based on the T-flops you are seeing, which is time-based floating operations per second. Good question. So these are sort of the 4 different core versions of distributed training. And what you can do with these is take what you need from them and combine them into what we call 2 and 3D parallelism. Now, one thing I will say, and this is something that I even got confused on when I was first learning distributed training, if we imagine these different algorithms as dimensions, right? Because we have combined them, we call it multidimensional parallelism. ZeRO and DDP are 2 halves of the same whole. So if you're using ZeRO or FSDP, because they're the same thing, with DDP, that is still data parallelism. It is not 2 separate parallelism strategies. They go hand in hand, which is why you can apply ZeRO to any of these situations, because it is a general data strategy, not in itself a parallelism strategy. However, say we could combine data parallelism with pipeline parallelism, and now we have 2-dimensional. And then we could add tensor parallelism on top of that, and then you get 3D parallelism with like what Megatron does or Nanotron. Now, for the fun part, so we're going to take a brief detour, and if you've been following the latest research, there might be a fancy term that you've heard of. DILOCO, making the news lately, and DILOCO and other variations of DILOCO. The general idea is, how do we train models across the globe in an efficient manner where, you know, we're running 100 gigabit Ethernet between one cluster in, say, Europe and another cluster in the US, right? We have to be real careful about how often we run communications, because ping rates are going to be astronomical, right? So the idea with DILOCO is similar to ZeRO2 sharding. Now, there's a bunch of fancy algorithms in place to make sure that it all works accordingly, but the general idea is you take your world and you split it up into neighborhoods. So we'll call this neighborhood 2 and neighborhood 1. And the idea being, in each neighborhood, you have an array of computers. And then in each of those computers, you know, they'll have 8 GPUs, and so forth. Same thing over in neighborhood 2. And the idea is sharding your model weights and limiting communication in such a way that these two neighborhoods can run independently for a decent chunk of time. And then every once in a while, they send their weights to each other. Generally, this is done asynchronously. And then you continue going, right? Well, this certainly sounds a whole lot like ZeRO 2, specifically ZeRO 2 hybrid, where the idea is you don't take a giant model and you shard it between nodes, you keep it local node, and then shard and communicate when you need to. And that's sort of the idea of how these decentralized training algorithms work. It is essentially on a very high conceptual level, how do you perform ZeRO 2 at a worldwide scale while also making sure that you're not having excess communications happening between models and limiting it to strictly the least amount of communications possible. So typically, these are going to wind up being solutions like model merging. So you let each neighborhood run independently for like 1,000 steps. And then you average those weights together every 1,000 steps or so asynchronously. So this one sends its weights over to here. This one sends its weights over to here. But they're still training while they're waiting for the other one to get their weights and whatnot. This way you have the minimum downtime possible while also keeping everyone relatively in line to as though this were happening all on the same node. Yes, Mert brought up there's an open source implementation of DILOCO by Prime Intellect. Yes, there is. And in fact, one of the authors will be speaking at the distributed training conference that's happening in September, which you guys will get a discount link for it after this in order to sign up. I also have more news about DILOCO when it comes to that. We're going to have a lot of fun at the conference with it. But for right now, that's all I can tell you. So this as a whole is the 4 overall distributed training strategies that are being used. I say 4 because I'm counting ZeRO as part of that. 5 counting DILOCO, but if you're not doing decentralized training on a global scale, typically you just use these 4. When it comes to inference with these, just to go a little more into that, typically you don't want to use ZeRO for that because ZeRO, right, is focused on sharding model weights, gradients, optimizer states, and during inference, you don't really care about that. Tensor parallelism can be good if you're serving gigantic models that like can't fit on a single GPU. Typically, though, you would end up using pipeline parallelism because it's the most efficient when you're running inference. If, say, you're trying to run pipeline parallelism, but you can't quite fit everything as it should be, you could run pipeline parallelism and tensor parallelism to serve bigger models at a faster throughput, given just a few extra communications that have to happen with the tensor parallelism that's occurring. But that as a whole is what we have going on. Let me know if there's any more questions. Otherwise, we're probably going to end up a little early, and that's okay. Not too worried about that. I would rather keep things short rather than us sitting here and accidentally taking an hour and a half. In the meantime, I will go ahead and just do a little plug. I'm doing a course which most of you are probably aware of called Scratch to Scale, where we're going to be implementing all of these algorithms from scratch. On top of that, there's over 14 guest speakers from various labs and specialized hardware libraries like Unsloth. Daniel Hand's going to be there. Tunji from the DeepSpeed team is going to be there. Sammy from Prime Intellect. Wen Chao from the TorchTitan team, and a few other folks that I'm still in the midst of chatting with. You guys will get a discount code for showing up today. It'll be 35% off to make this a bit easier. But it would be awesome if you guys would come. So Harshit asked a question of, does PyTorch support pipeline and tensor parallelism-based training on multi-node? Do we mean out of the box? Because yes, like that's what Nanotron does, for instance, in Megatron. PyTorch native, they have a framework, which I was actually going to go look at today, and we might do a lightning lesson called Torch dot, excuse my chicken scratch, distributed dot pippy. And essentially, we worked with the Torch team in order to help make pipeline parallelism as easy as doing device map equals auto in transformers. And so the idea being Torch pippy or distributed.pippy will take the device map from transformers and map it to a bubbling sort that, or a bubbling partition that pipeline parallelism will do, but automatically for you. So you don't need to know how you want to split the layer groups. We can figure it out for you based on what will fit in memory and conjoined layers that shouldn't really be split. And pippy can scale up to any number of nodes. It's a very general strategy. With tensor parallelism, still looking into that. Typically, TP is done through, actually, no. TP you would do through TorchTitan, which is the other half of it. TorchTitan is a 3D parallelism library that PyTorch is coming out with. Right now, it's still in alpha, so it's just called TorchTitan. And they sort of reworked how PyTorch thinks about distributed tensors and distributed training in order to make pre-training and training at gigantic scales easier to do. So TorchTitan and Nanotron both work in the same fashion of you define some config where you say, I want pipeline parallelism at a dimension of 4. I want data parallelism at a dimension of 2. And I want tensor parallelism at a dimension of 1. There's a really, really good picture in the UltraScale playbook that talks about this. But both of the frameworks work in this same way, where you define the config, set up your model how they expect, and then it will go run this 3D parallelism for you. If you just wanted to run pipeline parallelism, then you would just set everything else to 1. And Merc, it's not funny we have a guest speaker for TorchTitan. I did that intentionally because the idea for the conference is I wanted to get the people that are directly building these tools to help educate you because they're some of the smartest people in the globe on it. So that's why we have the creator of TorchPippy and DTensor speaking. That's why we have Fook from the Hugging Face Nanotron team who's going to be talking about FP8 because he recreated and implemented FP8 training from scratch to help speed up H100s and BH200 training when it comes to low precision. And I'm still working on getting a few others, so stay tuned for that one. But really, really good question. Otherwise, there's a specific problem which I can answer offline, but that's sort of everything in a nutshell when it comes to parallelism training and how each of the distributed strategies works. Essentially, your most valuable asset is not your GPUs. Your most valuable asset during training is the money you're spending on training. Communications, spend more money because you're training for longer. So, given that, reduce communications as much as you need to by utilizing these different strategies to get there. And that, as a whole, is distributed training. Reduce costs as much as possible by making things as fast as possible, and you're done. That comes from making sure your model is optimized for distributed training, as well as your data pipeline is optimized as much as possible to make data one of the smallest and least time-consuming processes in this whole thing. Because if getting your data is fast or is long, everything else becomes longer because you're waiting for the data. So, thanks for joining. These were wonderful questions. After this, I will share a less messy version of this diagram with you all, as well as some resources to TorchTitan and Nanotron and the DILOCO papers. But at this time, I'm going to try and do a talk on Thursday and make this twice a week. I just got to figure out a topic. If you guys have ideas, let me know. Ping me on Twitter. I have a question over there asking for ideas. In the meantime, I'll probably dig through some papers and see what fun things we can get into. But thank you guys for coming. This was a lot of fun, and I hope to see you guys in a few days. Thanks so much.